Welcome to calculus. Whatever confidence you have will be tested. But don't worry, Stevenson has tools to help you. On this episode, Stevenson will demonstrate. Now that we know we can find a derivative, which a function that's super helpful for us, we can't assume it always exists. So what are some examples of when it may not exist? So a function will not have a derivative at some point, a, f of a, where the slopes of the secant lines, fail to approach a limit as x approaches a. So there are four general scenarios that show these different instances when this will happen. So in each example, a function whose graph is otherwise smooth will fail to have a derivative at the point where the graph is. So there's four instances in when you can have a function that is not differentiable. It could still be continuous though. The first one is a corner. So the most common corner you can see here would be the absolute value function. So if you think about it, what are the derivatives to the right of 0? So this is the identity function, y equals x. So this slope would be positive 1. The slope on this side would be negative 1. So there's the corner at exactly x equals 0. So it's not differentiable at 0 because the left-hand and right-hand derivatives do not agree there. So if your graph has a corner, then you'll know it won't be differentiable at that point where they meet. Now, this is an example of something called a cusp. So in this particular case, if you look at the slopes on this side, these are approaching positive infinity. But if you look at the slopes from this side, these would be approaching a negative infinity. So when you look at what happens at 0, neither one of them actually agree. They're both headed off into an infinity. So this is not differentiable at 0. Again, the left-hand and the right-hand derivatives do not agree. Now, there's two more instances in which you can have examples of where a function cannot be differentiable. The third possible instance in where you can have a non-differentiable spot is if you have what's called a vertical tangent. So if you look at this function, this is the cube root of x, so it looks like an elongated kind of S. All the derivatives, all the tangents, and the slopes moving up to this point here would all be positive numbers. But at the exact moment x is 0, you're going to actually have a vertical line. And remember, the slope of vertical lines do not exist, are defined. And then if you go past 0, you're going to go back to having positive slopes. So this function is differentiable everywhere except at x equals 0 because the derivative, the slope, doesn't even exist there. Lastly, in 4, this is a discontinuity. So in a discontinuity, it makes pretty much sense why you couldn't be differentiable here at 0 because the function doesn't even exist there. So having a function be continuous is a requirement to entertain the idea that it could be differentiable. So just to recap, if you have some kind of a corner or a cusp or some kind of vertical tangent scenario at those values, then that means you will not be differentiable at that particular value. Now keep in mind, these three functions here are continuous. So don't assume something's continuous is automatically differentiable. In the fourth case, at any discontinuity, the derivative itself cannot exist. So later in this section, we'll prove a theorem that states that a function must be continuous at a in order to be differentiable. We actually talked about that a moment ago. And it'll be a quick and easy way to verify when something is or is not differentiable at a value. But how do we use this knowledge? So for example, it says find all the points in the domain of f of x equals the absolute value of x minus 2 plus 3, where f is not differentiable. Well, the solution is think graphically. What does this look like? If you remember parent functions and transformations, then you'll know this absolute value function is going to move 2 units to the right and up 3 units. So it's going to look something like this. It's still going to be the V shape of an absolute value, but the difference though is it's been shifted. It's been translated right and up. So when is this not differentiable at? It would not be differentiable at x equals 2. Okay, this point here, because that's where the corner is. So a lot of times when you're looking at where things are not differentiable, graphically is usually your best bet. If it's not graphical, then what we can do is we can actually look at the left and right hand limits of the derivatives and see why they don't agree.